We mentioned previously one of the bizarre aspects of quantum mechanics. The process of tunneling allows particles to penetrate barriers that are simply classically too high for them to overcome. This process is, however, actually nothing like the idea of digging a tunnel. There's no spade here, there's no hole that we dig, it's just not what's going on. And we're confronting here the common difficulty in quantum mechanics of finding words and analogies from everyday experience to describe quantum mechanical ideas. And we will often fail to come up with good words or good descriptions from what we see around us in our classical world as we try to explain quantum mechanics. It's not that we don't understand it, we just don't have the words to describe the things that we're talking about. There are many other surprising aspects of quantum mechanics, and as we start to learn quantum mechanics, we are confused when told, as we often will be, that some question simply does not have an answer. For example, we might think it perfectly reasonable to ask the question, as scientists did for several centuries, of whether light is composed of particles or waves. It would seem, according to our common sense, that it would have to be one or the other. But in fact, if we insist on this either-or answer, that is, that light must be definitely either a particle or a wave, then there actually is no answer to that question. The only answer we can give to it is that both of these, which is the idea of wave-particle duality, are simultaneously true. Another example is we might think it perfectly reasonable to ask what are the position and the momentum, or more loosely the speed, of some particle, such as an electron. Quantum mechanics will enigmatically reply to us that there is actually no answer to that question. We can know one or the other precisely, but not both at once. This particular enigma is an example of Heisenberg's uncertainty principle. Indeed, though it may seem bizarre, in the cases of both wave-particle duality and Heisenberg's uncertainty principle, in the quantum mechanical view of the world, there is no contradiction involved in either of these concepts. They are natural phenomena that lead to no confusions in quantum mechanics, at least if we separate them off from another and much more genuine difficulty called the measurement problem, to which we will return later. One of our natural human desires is to find causes and meanings in the things that we see around about us. These are part of the way that we construct models of reality that enable us to function efficiently as human beings. So as you learn quantum mechanics, you are likely to keep wanting to know the meaning of various terms and concepts as you work to construct your revised models of how things work. It's common and natural, therefore, for the student to ask what something means. However, I can warn you now that this is going to be quite frustrating at first. These interactions often take the following form. The student asks about the meaning of something in quantum mechanics, such as the uncertainty principle or the wave function or some other topic. And the professor or instructor replies with a question, "What was it you wanted to measure?" If you can tell me what you want to measure, we can figure out how to calculate that with quantum mechanics. And the student waits in vain for the professor to answer the question about what something means. This is also, and this is quite serious incidentally, called the shut up and calculate approach. Despite this, it is rather important as a student to at least try to frame these questions. Without, to some extent, fighting quantum mechanics and its ideas, you will never actually understand them properly. The more serious philosophical version of this approach is to assert that things that don't have meaning in science are the things that you can't measure, or if you can't measure them, you don't have meaning. This philosophical approach of dealing only with questions that can be answered by measurement, or that are purely logical questions within some formal system of logic, that approach is what is called logical positivism. We regard everything else as meaningless. If you can't measure it in the real physical world, it's meaningless. And it is the most common approach taken in dealing with quantum mechanics, at least at the elementary philosophical level. And by allowing university professors to dismiss most student questions themselves as meaningless, it saves a lot of time in teaching the subject. Now, one very substantial difficulty with this philosophical approach is that it is not clear in quantum mechanics what measurement actually is. Indeed, it can even be proved in at least one interpretation of quantum mechanics that you can't actually make a measurement in quantum mechanics. This whole issue is referred to as the measurement problem in quantum mechanics. And it is important to understand that the measurement problem is, in some people's opinion, really not satisfactorily resolved. You need to know that, because otherwise you may just think that somehow it is just that you are not smart enough to understand it, and that might cause you to give up. Actually, it is not clear if anyone is smart enough to understand it, so join the club. At least don't worry that somehow the problem is with you. The problem is not with you. This is a real and arguably unresolved problem in quantum mechanics. Now, if at this point you're raising an objection that there's an inconsistency in saying that quantum mechanics will only answer questions about things we can measure, but quantum mechanics cannot actually explain the process of measurement, you're quite justified in raising that objection. Now, what was it you wanted to measure?